Welcome. So, in this lesson, we are going to be getting into uh, PyTorch basics. Um, PyTorch basics, and basically, what we are going to be covering here is introduction to tensor and tensor operation. And this is going to be the first class in our deep learning series. So, in the previous series, we covered classical machine learning and we looked at several algorithms, several ways of building classical machine learning models that we can use to learn pattern from our data set. Covered linear regression, logistic regression, random forest, a lot of other models like that, gradient boosting and stuff. But in this half of the course, we are going to be learning about a very powerful concept called deep learning. So deep learning is basically the aspect of ML that is dedicated to building models that is structured in a way that takes inspiration from the human brain. So we build neural networks, we train neural networks to learn complexities from our data sets, right? And you're going to be seeing how this works, what a neural network is. A neural network is basically just kind of a model that has several interconnected neurons, interconnected layers that works almost kind of like the way the human brain works in a way. And one of the libraries that we use, in fact, the most popular library for training this neural network, for doing a lot of cool stuff with neural network is PyTorch. And the basic data structure in PyTorch is actually tensors. So that's what we want to be learning today. We are going to be seeing how the understanding tensors in PyTorch. So majority of the things that we are going to be doing, almost all of the things that we are going to be doing will involve tensor. So that's the reason why we must understand what it means. So this notebook is going to cover fundamental concepts in PyTorch, including tensor operation, and how to actually think of something called computational graph. So first thing we do is we import torch. So PyTorch is actually open to us to use via this library called Torch and it's PyTorch. So if you are coming from pandas, numpy, PyTorch is just torch. So there's no such thing as PyTorch. So it's torch. Now we're also going to import numpy because the way I like to think about it is, and I think that is the way it is really, but I'm not quite sure, is that PyTorch is basically, but yeah, but it's correct. PyTorch is basically NumPy just with extra functionality added to it. So extra functionality like what? Extra functionality like something called AutoGrad gives us the opportunity to do automatic gradient computation without having to do it manually, right? So that's what PyTorch um, gives to us, and we're going to be saying that. So we can run this. So these are the two libraries that we need, and you already know that you can always check the version of this and the torch dot thunder. Sorry, just to see if everything is properly installed. That should be thunder. So if we run that, we should get, yeah. So these are uh the current version of PyTorch that we are working on. So now let's get into the first aspect, which is tensor. So what's a tensor? Which is the main reason that we are here. So tensors are, like I said earlier, the fundamental data structure in PyTorch. They are like the same way arrays are the fundamental data structure in NumPy. But what it adds, what it gives us, the other thing that it gives us, the way that it's better than NumPy, is that it provides us with automatic gradient computation, so we can do differentiation automatically. And the whole thing that happens inside the neural network is just forward pass, which is basically matrix multiplication, and then back propagation, which is basically differentiation, which is basically calculus chain rule, which is what you're going to be seeing in the subsequent video. So instead of us having to do all of these things manually by ourselves, PyTorch has made it so much that a tensor can actually be differentiated. You can just call dot backwards and it just differentiates for you automatically, right? And apart from that, every other thing is basically almost the same thing that you'd have inside NumPy. So how do we create a tensor? So to create a tensor, we can create a tensor A, and that is going to be equals to, so whenever you want to create a tensor, you can go touch the tensor, and we're gonna have 1, 4, 5, 3, something like that. So we can check A, and we have tensor. A is this kind of tensor, right? So if I should do something like type A, the usual stuff, it says A is what? A touch uh dot tensor. A is a tensor. And this A is actually one dimensional, right? So it's a one dimensional tensor. And this is something you'd call a vector. And another thing is you can actually have a tensor as a scalar. So let's say, for example, I can come here and say one dimensional tensor, and aka this is a vector. Another thing that we can have is, okay, let's come here and add, let's add one more here, here, creating a tensor. So second thing that we're going to add is a 2D tensor, which is basically a matrix. So we can say some underscore matrix, let's call it that. It's going to be equals to torch dot tensor, excuse me, and we can pass in our 2D array here. So we have this, I can go like this, then to make it easier for us to understand, I can go 2, 5, or 2, 6, 4, 1, maybe even add one more, 3, then I can come here and do 2. So this is just me trying to make it clear. I can actually just do it like this, and like this. I don't like the fact that it's formatted in a weird way. This is wrong, and like this. Yeah, perfect. So take this to the next line. Yeah, this is perfect. So if we come here and say some underscore matrix, we have a tensor like this, and this is if I should do type of some matrix, we have touched on tensor, easy stuff. So this is a matrix and this is a vector. And you can have a scalar also. You can have a scalar, and that's going to be a unit tensor. That's going to be scalar. So what does that mean? I can do some scalar equals touch.tensor. Basically, what we've been doing here since, you can actually just do touch.tensor data. So the first value here is data, right? So I can do data equals maybe 5, and we can do some scalar, and it says tensor of 5, and this right here is a scalar. It doesn't have any dimension, it is just a unit tensor. So again, this is a scalar, or you might not even pass data. If you want, just pass your normal 5. Cool. So this is a scalar, this is a matrix, two-dimensional, and one-dimensional is a vector. A one-dimensional tensor is a vector, two-dimensional vector is a matrix, a unit tensor is a scalar. So that's how we create tensors. And we can also create tensors with different data types, right? What does that mean? For example, I can come here and say, for example, for this sum matrix that we created here, should I just copy that so that we don't have to type so much? Let me just copy this. If I do touch the tensor, let's do this so that it's on the same line. Yeah. So I can say data equals this, and I can actually do I can specify from this doc string that you see, I can specify data type. So I can say the type, because if I do the type equals touch dot float, float 32 bits float. It says sum matrix, and I run that. Now all of these now have point, 2 points, so 2.0, 6.0, 2.0 again, 4.0, because I said this should be of the type float. I should come here and say touch dot long, everything remains as integer. Dot long is integer. I think there is integer 32 also. Integer 32, and it's going to work like this. Can you see? So data type is integer now. So basically, and you can do 64 bits integer. It's the same thing really in terms of how you are going to see the value here. But I think the difference is in the representation in memory. So you can do integer, you can do float, and all of that. That is, you can create a tensor that that conforms with a particular data type that you choose. Right. Another thing that we can do is, which I feel is the next thing to look at after learning um, the different type of tensors that we have based on dimension. Another thing that we can actually learn is creating tensor based on shapes, right? So, and we are going to be looking at different two-dimensional tensors. I want to say creating different two-dimensional matrices with different um, shapes, right? So, for example, we can create a 2 by 3 um let's see 2 by 3 tensor. That's going to be, we can do some, I'm running out of variable names to use. Let's just say x. So x is going to be equals to touch the tensor, and we're going to have 2 rows, 3 columns. So we can go 2, 3, maybe 2, 3, 4, 1, 5, 6. And if we print out x, it says, oh, yeah, that's true. We need an extra bracket here. Ah, excuse me. Perfect. So we have our 2 by 3 um, tensor. And if you want to actually create that with random numbers, we can go random underscore x. That is, we want to create a kind of tensor like this, but with random numbers. I think it's 3 by 2, not 2 by 3. So you can go touch dot rand, not touch the tensor, touch the rand. Perfect. And we can specify the way we want it to rand it 2 by 3. So if I say random, if I print random x now, we're going to have this kind of tensor that we created earlier, this 2 by 3 tensor. Right. So, but this one in this case is getting filled with random numbers. So we have row 1 and row 2. Now I can print this x just to show that this is the first one. So this is the first one for x that we created, and this is the second one for some random x that we created, a 2 by 3. Now, another thing that we can do is we can also randomly, we can, that's not random, we can generate zeros, um, tensor of zeros. And how does that work? We can actually say some zeros, that's going to be touch dot zero, I think. Yeah, touch dot zeros, not zero. And how do we want it to go? Let's go 2 by 3. And we can actually, let me add print here so that this gets outputted also. And I can come here and print out some zeros, and oof, that's a mistake, some zeros, and run this. So I have a 2 by 3 matrix of just zeros, right? So that is how we create tensors. And another important thing is, if we use rand, and these are things that you can check in their documentation. So if you go into PyTorch, let me show you, there's PyTorch documentation that you can always go check later. Everything that we are going to be covering in this course is usually just is inside this doc, and it's a very beautiful detailed doc that you can go through. So what I want to actually mention now, so for example, majority of the things that we've been talking about, that we are also going to be talking about, are not even the doc covers way more things than we can cover over the entirety of this course. So what I want to bring out is this particular guy here, this one that we got with touched or rand. This guy actually returns a uniformly distributed random numbers, that is random numbers between 0 and 1, right? So if we want to print out, if we want to create tensor for some normally distributed random numbers, so we can say some norm, you can name it anything, tensor, that's going to be touch dot rand n, I think. Yes, rand n. And if we go 3 comma 3, we are saying give us a 3 comma 3 matrix of normally distributed random numbers. So if we do this, so we see that now this is a matrix of randomly distributed um, of normally distributed random numbers. So you can see that this spills out of 0 and 1, like this is greater than 1, this is lesser than 0, right? Then you can also do dot rand int, like you want to get random integer sum int tensor, and you're going to be torch dot rand int. Perfect. And you can go 2 3 if you want. It says argument size must be a tuple, not int. Okay, I think this expects a tuple. Let's check here. Okay, that's weird because we already there is low and high. So it says filled with random integers and enter uniformly between low and okay. Let's go low equals 2. That it starts from low. I equals maybe 5, and we can go size equals, if size is what I'm guessing size is, okay, size is a tuple, the shape of the output then, so okay, so that's going to be 2 3. So if we run that and that works, so we just need to print it out, sum underscore int underscore tensor. So it gives us a random integer between 2 and 5, and the tuple is the size of the output tensor is going to be 2 3. 2 rows, row 1, row 2, 3 columns, like that. So that's basically creating tensor, right? There are still other different ways that you can create tensor that you need to find that there is a way to create identity tensor. You are coming from math, there is identity matrix, and if I can say identity underscore tensor, and that's going to be equals to touch dot I, right? So if I want to create a 3 by 3 identity matrix, sorry, we have to print that out. Say identity tensor like this. So we're going to have this identity matrix here, and identity matrix is only going to have ones in the leading diagonal here, right? And it comes in handy when you are solving problems like eigenvalues and things like that. So yeah, that is that. You can also create tensor within a range, stuff like that that you find inside the doc here, and that we are also going to be doing. We're going to be using them when we have a need for it. But these are just like the basics. Now, the next thing that we are going to be looking at is, tensor attributes. Some. I'm going to add here and say some. Tensor attributes. So we are going to take, let's say we're going to be taking some of the tensors that we've created. So if I should print out which one? Okay, some integer tensor, some int tensor, this one. Let's take this particular tensor here. So if we want to like get the shape of this tensor, we can do, let me just do it first. We are going to do some int tensor, just like numpy dot shape. And it's telling us that this int tensor is what? A 2 by 3 tensor. So I can print like that, right? And that is how we get dimension of our tensor. So the other thing is we can actually get the size of the tensor. So we can go say print some int tensor dot size. So if we do some int tensor dot size, what do we return? We also get the dimension of our The shape, not dimension really, the shape of, let's put it that way, shape, because dimension will mean another thing really, because there is touch dot dim. So this also return like kind of like the shape. Then we can print some some int tensor dot dim, and if we run that, so this is two-dimensional. Our tensor is two-dimensional, and why? It's a matrix. It has rows and columns, right? Two-dimensional. So that's basically some of the attributes, some of the popular attributes. There's still like dot the type, the regular things that you have in NumPy. If you understand, if you have a very solid understanding of NumPy, then this should make more sense to you. So if I do some int tensor dot the type, and the type is an attribute actually. This is a method, size is a method, dim is a method, shape is an attribute too. But probably we should say this one some attributes and methods. I think that's the right thing to say. So the type is an attribute too. If we run that, it says the data type of some int tensor is what? All integer 64. So that is that. Now, what is the next thing that we're going to be looking at now? The next thing that we're going to be looking at is some tensor operation. We're going to be looking at some tensor operations. What are the things? Or before we do tensor operations, let's actually look at, yeah. Let's do tensor operation. So, what is the first thing that we're going to be looking at under tensor operation? The first thing is we're going to be seeing how do we slice and index tensors. How do we actually slice and index tensors? So let's create a tensor from scratch. We're going to have a tensor A, and we're going to say A is going to be touch.tensor, and it is going to be a 3 by 3. So let's say we have 2, 3, 4, 5, 6, 7, something like that. Then maybe 8, 9, 10, 1. That's fine. Now let's print it out. Print A. So these are a 3 by 3 tensor. So let's slice it. So the first thing we're going to be doing is slicing a tensor. So it is let's start with indexing. Sorry, indexing is an easier concept that kind of relies on that slicing relies on. So how do we index a tensor? So if I should print out a like this 0, 0, and I run this, I have what? 2. What does that mean? Position row 0, column 0. Kind of like this is row 0, row 1, row 2, and this is column 1, and column 0, column 1, column 2. So if I should print out, let's say 2, 3, I get what? I'm sorry, a a 2, 3. Yeah. A 1, 2, excuse me. 3 is out of range. Python starts counting from 0. That is my mistake. So that is 7. So what are we saying? We are saying row 1. Where is row 1? Well, this is row 0. This is row 1. Then where's column 2? Column 0, column 1, then column 2, making 7 the element in that position. So we want to see, let's say you want to print out 9. That's going to be what? Row 2, column 1. Row 2, column 1, because 0, 1, 2, then 0, 1, like that. So that's how you index. You index almost like the way you do, you reference elements in matrices. So yeah, let us see slicing, and there's no important, there's nothing special in this. Let's see slicing a tensor. How do we slice a tensor? So let's say we want to get out the first column, right? We want to get out the first column. So how do we do that? Do print. You're going to go A, and you start with your column that like get everything in the first row. So if we run that, we are going to get 258. Basically, what we are saying is get everything in the first column. Sorry, not first row. Get everything in the first column, right? And the second thing here is okay. Let me say, let me add comment. Print first column. Another thing that we could try and get is we could maybe get, let's print out this second row. Let's print out the second row. So how do we do that? We are going to say print. We can go A and we can go 1. That's going to be first row, and this is how you do it. And if you run that, excuse me, I'm going to have what 567. This particular line here, and you can further do much slicing. For example, if I show you this, it's going to be 234. Like put 0 there. If you do 2, that's going to be 891, which is the last row, right? Now let me just add print last row. Now the next thing that we are now going to do is, if we want to actually print a subset of the matrix, let's say we want to print this 6791, or we want to print this upper top right 2356 or 347, or just anyone at all. How can we do that? So we can actually do like print. Let's say we want to print out this top right 2 by 2, right? This particular top right 2 by 2, this place. So how do we do that? We can say print A, that's going to be 0 to 2, comma 1 to 3. That is going to correspond with the top right. So I'm going to say top right 2 by 2. So what do we have? We have 3 4, this top right here, 3 4 6 7. Basically, what are we saying? We are saying give us 0 to 2 and give us 1 to 3, right? So you can also like slice anything you want, you can index anything you want, and apart from, in my opinion, apart from not even that, everything here takes, apart from this particular index, you don't do indexing like this in a list. Majority of the other things are in a list or non-hierarchy. The other things that you can do really that we are doing here, they are consistent with how it is in a non-hierarchy, right? So yeah, that is that on indexing. So let us move on to some other operations, that is not indexing only. So we're going to be looking at arithmetic operations. So let's look at arithmetic operations. So if we have two, I think, what did we name this one? Let's call this one x then. So x equals torch dot tensor, and we have this tensor of 2 3 4, and we have maybe y and torch of 4 5 6, and like that. Or 567 to be. Now we can actually add these two tensors together in two ways. We can, obviously do something like a plus b, just x plus y. If we do that, we have 7, 9, 11. Element wise addition: 2 plus 5, 7, 3 plus 6, 9, 4 plus 7, 11. And we can also do this by doing touch.add. The touch.add x comma y returns the same thing. And we can do subtraction, print x minus y. We get, that's interesting. So all of them, they have 3. So 2 minus 5, 3, 3 minus 6, 3. So we print touch.sub x comma y, the same thing. Then, so that does element wise subtraction. Then the next thing is element wise multiplication. So I say addition. This is subtraction. And this is the next one is going to be element wise product or multiplication. So how do we do that? Just the normal asterisk. So we can say print x asterisk y. That's going to be 2 times 5, 10, 3 times 6, 18, 4 times 7, 28. Or we can say print torch.mul, basically short form for multiplication, x comma y. And that is going to do element wise multiplication. Then, division also can do division. That's going to be print x forward slash y. And you can also do touch.div, short for divide. Perfect. So the other thing that we can now actually focus on is, apart from the simple element wise products here, element wise multiplication, we can actually do element actual matrix multiplication. And like I mentioned earlier, the bulk of the interesting things that happen in neural network is always just forward pass, which is matrix multiplication, and back propagation, which is calculus. So which is chain rule rather. So we want to see how to actually do matrix multiplication. So how do we do matrix multiplication? We use mathmul. We use mathmul or the asterisk sign. So I can come here and say, sorry, matrix multiplication. So we are still going to be using these two guys. So I can say print x, y like this. And what we have is, hold on. Let me, oh, sorry. Yeah, that looks good to me. Why do we have, hold on, let's check touch.mathmul, touch.mathmul. Yeah. Then we go x comma y. 56. Hold on. Let's check our x. What's inside x? Oh, yeah, that's true. That's true. I was thinking x is a 3 by 3 matrix. This is correct. So the way matrix multiplication works inside the way matrix multiplication works generally is that a row we multiply a column. So how did we arrive at this 256? The way we arrived at this 256 is 2 times 5, 10, plus um 3 times 6, that's going to be, what's that, 18, then plus 4 times 7, 28. So that should give you 56. So like the number for two matrices to be able to multiply each other, they must either be both square matrices, or the number of rows in matrix A must be equal to the number of columns in matrix B. So what actually threw me off earlier is because I was thinking X and Y are like 2 by 2 matrix or something, 3 by 3 matrix. So let's create something like that. So we can say A equals, let's say 2, 1, um, A equals 2, 1, 1, 3. Then we can come here and say B equals 2, 4, 1, 4. Something like that. So I can take this to the next line. Maybe even just do one line. Don't know why I keep doing multiple lines. So if I should do print A times B, A multiplied by B, which is going to be matrix multiplication, and also do print A comma B. Now this is going to return a 2 by 2 matrix. We have an error. It says unsupported. Oh, sorry. Torch.tensor. I am actually rushing through this. Torch.tensor, and here also is going to be torch.tensor. Perfect. So this returns matrix multiplication, right? So how did we come about this 5 here? So this 5 is going to be, if you actually print out, let me print out A and B for us here, so that we can actually get a mental picture of how this thing is doing the multiplication. So this is row 1 in matrix A, and this is column 1 in matrix B. So to get the element here, that's going to be this row 1 multiplied by column 1. So that's going to be 2 times 1 plus 2 times 2. That's wrong. That is this multiplied by this plus this multiplied by this plus 1 times 1. 5. That is how we got the 5 here. Then for something like, how did we come about this 16? So this 16 is this multiplied by this. So that's basically 1 times, if I'm correct, 1 times 4 multiplied by 3 times 4. That is right one, 16. So that is how matrix multiplication works, and that is what we are doing using either this @ sign or touch.mathmul. Right. So that is that. So the other thing, that there are a lot of things that you can do. You can do determinants, and it is easy to do. Just call touch.det, det. You can actually get inverse also by getting touch.inv dot inverse. Actually, you write the dot inverse. You know, a lot of good things that you can do. Touch your max, touch your min, stuff like that. But I don't want this video to be too lengthy. So the last thing I'm going to be doing, and as a matter of fact, majority of the things that um we haven't really touched on here, if they are important, we are going to be touching on them. We are going to be having a use for them in the next one. But the ones I'm covering really are things that are really, really important that you should know beforehand. So the next thing we are going to be looking at is actually a computational graph. Excuse me, computational graph. So how does computational graphs work? How does automatic gradient automatic gradient computation, how does it work? How does this thing help us to actually compute gradients and help us train neural networks and stuff like that? So this is the way that works. For example, let's say we have two variables x equals, let's say, torch.grad, torch.tensor, sorry. Let's create the tensor first. So we can say torch.tensor, and let's say this tensor is a scalar, and you must always make it a float. If you don't, it's going to throw an error. Let me say it requires grad. You must set requires grad equals true. That's your way of telling this guy that this should be differentiable. That is, this guy should track gradients for us. We say touch the tensor again, and I say 3, and I set requires grad equals true again. If I run this, it's going to throw an error. Yeah. It's going to say only tensors of floating point and complex data type can require gradients. So point 0, point 0. So if I run this, it works. So you should always add point 0, right? Now, if I have a um a function, let's say y equals, let's just say 3, y equals 2x squared, 2 multiplied by x star star 2, 2x squared. Now it means that for, you know the relation between y and x is that y is equal to 2x squared. That is, when y equals something like 1, 2x squared, when x equals to 1, y is going to be equals to 2. When x equals to 2, y is going to be equals to 8, and on like that. So this particular relationship, um we can differentiate it, from our knowledge of calculus. And if you differentiate 2x squared, what are we going to have? We're going to have 4x, right? So it is the same that we can do here. And how can we do that? We can say, um no, this shouldn't be y, this should be z, because y is already having its own equation here, its own value here. So we can say z dot backward. So if we call z dot backward, what does it do? It computes dz dx. That is the derivative of z with respect to x. So if we do that and run this, it has worked. Now, if we have dz dx and z is 2x raised to the power 2, so when x equals to 2, what is going to be dz dx? Dz dx when x is equals to 2 should be 8. Why? Because dz dx normally is 2x squared, that is 4x, then 4 times 2. So if I come here and say x dot grad, that should print out 8 for us. So this is 8. If we do the same thing for, let's say we have z as another function of y. So um, let's say we have them together here. So let's say 2x squared plus 5y, 5 multiplied by y star star 3, something like that. So we are saying z equals 2x squared plus 5y cube. Now if we run this z dot backward, now if we want to check y dot grad, What is y dot graph going to print? Before we print it out, let's try and calculate it. So, this is going to be partial derivative. So all of this is going to be treated as a constant. No, no, no. All of this is going to be treated as a constant, and we're only going to differentiate 5y cube. So 5y cube is going to be what? 3 multiplied by 5, that's going to be 15, 15y squared. So 15y squared when y equals to 3. 3 squared is 9. Let's put that here. 3 squared is 9. 9 multiplied by 15, that's 135. So this should be 135 if my simple math is correct. Correct. So this is 135. So that is how um this guy helps us. And if we have something like plus 650 here, it will not change the values because the derivative of a constant is 0, right? So this still remains 135. But if I should add something like plus 2y plus 2 multiplied by y here, so that becomes what? That becomes, that makes y into 137. So I should run that, and run that, and run this again. So y becomes 137. So that is basically what this guy helps us to do, gradient computation. Right. So for us to do gradient computation. So that is basically, and what we call is what? This dot backward. This dot backward. That is what helps us. So it says compute gradient of current tensor with respect to the graph leaves. So the graph is differentiated using chain rule if the tensor is non-scalar and all of that. And this is like a core idea in neural network basically. So that is that on PyTorch introduction, tensor basics. I'm going to see you in the next one. Bye.